Okay, here we are, part two now. Now we're after we've done we just to backtrack a little bit, we imported all the libraries and we had the sequential convolutional 2D, max pooling, flatten, and dense. All these layers that these have the libraries that we need to get to make the layers for our convolutional neural network. Initialize our CNN with the sequential and stored it in a variable called classifier. Okay, and then we're just kind of designing the. We just did the convolutional layer last time. Now we're going to do the pooling layer. Remember the pooling layer? What is it? What is it now? It consists of reducing the size. We just kind of keep reducing the size of it, taking the most essential elements of the every feature of the input image, and with another feature map called the pooled feature map. With each stride, essentially what we're doing is we're taking the minimum value inside each feature map, and sorry, the maximum value, not the minimum, but the maximum. And why do we do this? Why do we do this? Well, because we want to reduce the number of nodes that go into the flattening layer, which is the next after this. We want to try to save as much compute time as we can, but saving the most essential elements. You'll find that computer science, and if you ever take a course on algorithm and design analysis, it's all about trying to make. It's a study of algorithms and how they work, and how computer scientists many years ago try to make algorithms better, and how we design them better. Better in computer science means saving room and making it faster. Okay, that's basically what it is, because time is money and so forth. We want to what was I now? So to get the flattening layer, we want to after this we will don't want to reduce. Then what we want to do is we actually want to everything next after this is going to be highly compute intensive. So what we want to do is to avoid this is we want to make a pooling layer, and we're just going to follow along and keep using our classifier variable. And again, the max pooling, this hyperparameter here, choose a 2x2. This is just how big we want to make the pooling. Sorry, the feature filter. How big we want to make it. There's a default size, and then there's if you want to play around with how big you want to make it. It really depends on the input image and how we'll kind of dictate rather what how big the pooling size is. By the way, if you ever want to know how like the parameters arguments that you need to make, you need to put inside of a function, you just go before it, hit Control I on Windows. I can't remember what it is on Mac computers. I think it's Control or Shift some other thing, and it'll show you what kinds of the arguments that you put. Self obviously is the standard argument when we initialize something. We won't need to do that now. And of course the layer, which is the max pooling layer that we're going to use. Okay. So once we have that done, we highlight it and it's in. Okay, so good to go. And then next is the flattening layer. Okay, and the flattening layer. This takes essentially, what does it do, right? Remember, we have the pooling layer, so it takes all of those, takes all the pooled feature maps, all right, and puts them into one feature vector array for classification. And this layer is going to be our input layer for our ANN. So we're going to just continue on with using our little object here, or variable that we created. Sorry, it's kind of hard to type and talk at the same time, so if I don't make sense sometimes, you'll know why, and record this video. So that's good to go. No really need to put any parameters in this. We just use the default parameters. Okay, and we're going to use that. Highlight that, and then here it is. Okay, so it's all flattened. The images are all flattened, ready to go. Okay, so in order to save some time here, I kind of just went and did step 4. This is the fully connected layer, the last part, the CNN called the ANN. So just to kind of give you a little bit of a comparison analysis here and where we are exactly. So essentially we're just at the flattening layer and we're about to go inside to the ANN layer here, the fully connected layer, which is this one right here, into the classification. Okay, so we went through this as the input image, we made all the feature filters and went through it, pixel by pixel, and then we did the pooling layer, flattening layer, and then we're now into the fully connected layer. Okay, so now the classifier, the full connection layer, this is how many nodes essentially we're going to be using here. I put in 128. Again, this is a hyperparameter that you can utilize. You can play around with this number. You might get more accurate results when we start doing the learning, and you'll see how the accuracy rating is going to go up and down. And it really depends. You can use 200 nodes, you can use 300, you can use 20. So, but this is important here. We need to make sure that the activation function here is the rectified linear unit. Sorry, the activation function is a rectified linear unit for the first step here. Okay, so when they go through the first layers, we're going to use the ReLU activation function. Because this is a binary type of classification that is dogs or cats. It's just two of them. If there are several types of classifications, then we can use different types of functions. Like what they call TAL functions and so forth. But right now we're using the sigmoid, which is good for just binary classification. Okay, so make sure that you have this as a second layer for the sigmoid. Okay, and then once you have this, what we're going to do is we're going to highlight this, run it, and then everything went through. Now what we need to do is actually compile the classifier and choosing the correct optimization and loss function too, which we're going to do here. So now we did all that. We're going to again use our little object here that we did and compile. Right here it comes up already for me, so I'm just going to click that. We actually want to use the compile function. Okay, oops, sorry. You can see the arguments came up itself. Self optimizer is what I'm trying to type in here. So okay, and just remember the optimizer that we're going to use, the most important one here is Atom. There's other ones that you can use here, but Atom is the most, I can't remember the acronym that stands for something, I can't remember off the top of my head. But because, again, this is a binary classification, we're going to be using the binary cross entropy loss function here. And the metrics that we're going to use for binary outcome, we need to have more than just dogs or cats. But since it's not, we're just going to be using the metrics accuracy. So when we have all that, we're going to compile and run that, and good to go. Everything's in. And in the next video, what we're going to do is we're going to actually run it. You're going to see everything start to when it goes to the data. You're going to see the accuracy go up and down, and you can actually see it learning in the process. And just stay tuned for that. Okay.